What if your application could remember not just the current conversation, but also maintain persistent knowledge across all user sessions? We'll see how LangGraph state management combines typed state definitions with reducers to handle both thread-specific and cross-thread data. You'll watch how the annotated list SDR, add, pattern creates a channel that accumulates values across nodes, while the store system maintains user-specific memories that persist beyond individual conversations.
From typing, import annotated. From typing extensions, import type dict. From operator, import add. Class state type dict. Foo, int. Bar, annotated list SDR, add.
This demonstrates the stateful workflow pattern with persistent checkpoints, a core technique for building resilient, interruptible systems. The concept revolves around capturing the complete state of a computation at discrete steps, allowing you to pause, inspect, or resume execution from any checkpoint. What makes this distinctive is the separation between the workflow logic and its execution history, enabling features like time travel debugging, fault tolerance, and human-in-the-loop interventions without modifying the underlying graph structure. The pattern works by treating state as an immutable snapshot at each superstep, where a checkpointer persists the state graph, pending writes, and execution metadata to durable storage. This creates a linear history of threads, each representing a conversation or workflow instance, where state transitions are atomic and replayable. The declarative nature of the state schema, with reducers like annotated list SDR, add, ensures predictable state evolution, while the checkpointer's storage-agnostic interface allows swapping between in-memory, SQLite, or Postgres backends without changing application code. This approach solves three critical problems in long-running or interactive systems: recoverability after failures, auditability of execution history, and interactivity for human oversight. It's particularly valuable in agentic workflows, multi-step approvals, or debugging complex pipelines where you need to inspect intermediate states. The trade-off is storage overhead for checkpoints, but the flexibility to replay, fork, or introspect workflows often outweighs the cost, especially in production systems where reliability and observability are non-negotiable. Let's break it down line by line.
From typing, import annotated.
Imports annotated from Python's typing module, enabling metadata attachment to type hints. This allows adding context to types without affecting runtime behavior, crucial for the bar field's custom annotation later.
From typing extensions, import type dict.
Imports typed dict from typing extensions, which enables type-check dictionaries with fixed key sets. This is essential for defining the state structure with explicit field types, ensuring type safety for the state management pattern.
From operator, import add.
Imports Python's built-in add function from the operator module. This will be used later as a metadata annotation for the bar field, indicating that list concatenation should use addition semantics.
Class state type dict.
This defines a state typed dict where bar is an append-only list of strings. The annotated list SDR, add, annotation specifies that when multiple nodes return values for bar, they'll be merged using operator add list concatenation rather than overwritten, enabling cumulative state updates across graph nodes. State management with reducers in LangGraph. This pattern demonstrates how typed dict with annotated types and reducer functions like operator add enables controlled state updates, where specific fields can accumulate values rather than being overwritten. The reducer only applies when the annotated key is updated, leaving other state fields to follow default overwrite behavior. Precision in state mutation logic eliminates ambiguity when nodes return partial updates, making complex workflows more predictable.
The reducer that adds nothing preserves everything.